Yeah, today we're very happy to have Sap here to talk about chasing small set. And he is an expert on online optimization. And yeah, you can start.
Thanks, Intet. So as I said before, it would be really great if we made this talk interactive. So please ask me questions. I don't know how easy it is for you in the room to ask questions. So maybe you raise your hand or something and somebody gives you a mic. I'm not sure, but please.
We have the technology. It's okay.
Wonderful. That's great. Thanks, Daniel. So please really do ask questions. Okay, do slow me down. Otherwise, it might go by a little bit fast. Okay, so as you see on this title slide, I want to tell you about chasing small sets, or at least this is the abstract that I sent and the title that I sent. But unfortunately, we don't quite know how to do that yet. So instead, what I'm going to tell you about is a survey of what we've been doing on this topic of chasing over the past 5 years. And, I'm going to talk about chasing small sets. This will be towards the end, and, why it's difficult and what are the, difficulties there. So I will tell you about those 3 phases in our work. So it's a little bit like, in the Marvel cinematic universe, phase 1, phase 2, phase 3, with, lots of different heroes. So, phase 1 was Michael Cohen, James Lee, Yintat Lee, and Alexander Madry. Phase 2 is Boaz Klartag, Yintat again, Yon Julie, and Mark Selke. So you see there is some memory in the process. Yintat was phase 1 and phase 2, and then phase 3, Mark Selke is coming back with Niv, Bo Binder, Christian Poester, and Yuval Rabbani. And if I were there in person with you guys, I would be happy, maybe over drinks to tell you, which how do you map these people to the heroes in Marvel, but maybe I'm not going to do that while I'm recorded. Happy to do it in person. Okay, cool. So let's get started. So I'm going to tell you about chasing problems. So what are chasing problems? They can be phrased like this. So the data, what the algorithms designer has in his hands is a metric space X and a set system S in X. This is all. This is what's given to you. You have this metric space, maybe finite, maybe infinite, doesn't matter. And you have a set of sets in X. Now you're going to play a game against an adversary. So the adversary also knows this data. And what the adversary will do is that the adversary will select a sequence of sets in advance, S1, S2, etc. Up to S capital T, let's say, if we play capital T rounds. So this is what the adversary does, and the player does not know the selection of sets. Now, what the chaser will do is that sequentially, those sets are going to be revealed. So at each discrete time step T, the set ST is revealed, and what the chaser has to do is to pick one element in this set. Okay, so it has to select one element in this set, and that's it. Then the next day comes, a new set is revealed, and the person has to choose a new element in that set. And we're going to allow randomization. Okay, so we're going to choose an element row T in ST, and this choice is going to be at random. Okay, so very important. I'm not going to talk about deterministic algorithms almost at all. I'm focusing everything on randomized algorithm. I want to know, what happens with randomization. Okay, so that's the game. Now, what are you trying to optimize? As always, there is some, reward function or performance measure. So your cost is simply your movement cost. So, you selected an element in the previous set. Now you select an element in the new set. And what you're going to pay is the distance between those 2 elements. Okay, and your total cost is going to be the sum of the total movement that you've done. And the performance measure that we're going to look at is the competitive ratio, which, was already introduced, at least in the 2 previous talks, and I'm sure many times during the week. So the performance measure is a competitive ratio, which is, how much more you have paid compared to the best you could have done in hindsight. So if you knew in advance the sequence of set S1, S2 up to S capital T, then there is some amount that you could have done, some amount of movement, and you want to know, did you pay much more than that? Okay, so I'm not gonna talk at all about applications, what this setting really means, etc. This is kind of the given for the next 50 minutes. We want to understand this setting. Let me maybe just say as you can imagine, this is so basic, so general, that it covers a lot of things that we're doing in online algorithms. Okay, for example, case servers that you just heard in Anupam's talk, that's one example of a chasing problem where really your metric space is, you know, your set of configuration. So you have, you know, your case servers, they are in k location in some, you know, base metric space, and now the capital X is just the set of, an element in capital X is a configuration, and the distance is the Earth mover distance, the Wasserstein distance. Okay, and in that case, the set system in case server, notice that the set system is very interesting. It's just singletons. Okay, you just want to say, I want to be in that location. Okay, I want to have one server at that requested location. Okay, so sometimes the set system can be very, very simple, but the fact that the metric space is complicated, that might, you know, lead to a lot of difficulties. Okay, so we're going to talk about this basic scenario, but we'll also talk about variants, and I will explain why I put it in quotation marks. So the first variant is, instead of having one server, you can have, instead of having one chaser, you can have k chasers, such as k server. Now, why do I say variant? It's because it's really a different parametrization. You know, for k server, you can phrase it like this, where you know, your state, an element in your metric space, again, is a configuration, and the set system is not really, you know, singletons. It's, I need to have one server in this location, and the other server can be anywhere. Now, in the version where I claim it's a variant, when we have k chaser, then the metric space is a base metric space, where we don't have the Wasserstein distance, and the set system is a set of singletons. So you see, I did not generalize anything with this variant. It's just a different parametrization, and maybe in this different parametrization, you know, some things might be simpler. All right, so it's not truly a variant, but it's just a different parametrization. Another variant, which this one is a true variant, is that sometimes, you know, you might want to look at the same problem, but where some movements are free. So the canonical example here from the literature is k-taxi. So let me remind you what is k-taxi. So it's exactly like in k-server. You have k-servers, you know, they are at some locations in your metric space. Then there is one point which is requested. You have to choose one server to send to this requested point. But then once your server arrives at this requested location, you know, this is a taxi coming to pick up a person. Now this person wants to go from this location to another location. So the server is going to move from point A to point B, and you want this movement to be free. Why do you want this movement to be free? Because this movement of picking up the person from A and, you know, getting that person to location B, any algorithm must pay that movement. You know, whether you opt or, you know, the online algorithm, everybody wants to pay it. So, you know, we don't want to include that in our comparison, you know, for the cost of not knowing in hindsight what was the sequence of requests. All right, so it is much harder when you have free movements, and we're gonna talk about what happens beyond k-taxi. You know, to me, k-taxi is just one example where you have free movement. Another variant, and again, quotation mark, because, and this is non-trivial, it does not generalize what's written above, but it's, again, a different parametrization, is instead of chasing sets, you might want to chase functions. And here, maybe applications in your mind will come up more naturally, especially if there are people in the audience who are more versed in, you know, optimization or, you know, even machine learning, and I think many of you are. So in chasing functions, instead of a set as a request, you get a cost function CT as a request. So CT is a function from X to R, right? Let's get started by writing some stuff. So CT is from X to R, okay? So to maybe R plus even. So to every location, it's giving you, you know, some cost. And what you're gonna do now is that your cost, your total cost is gonna be the sum of two terms. It's gonna be the movement cost and the service cost. Meaning you were in the state rho t minus 1. Now you get a new cost function, which in the literature is called a task. Okay, so you get a task which is represented as a cost function on your state space, and you have to complete this task. Now you were in a certain state. What you can do is you can update your state. You're going to pay the movement to update your state. Now you're in a new state, and you're going to complete that task in this new state. So you're going to pay CT at rho t. Rho t is the new state. Okay, so this is, again, it's non-trivial, but I'm telling you it's not a generalization of the above. You know, the above covers that case too, but again, it's a different parameterization, and under that parameterization, some things might be easier than others. So when I say it's not a generalization, let me give you one example, maybe that, you know, to set everything in your mind. If I'm looking at convex sets, okay, so let's say my metric space capital X is Euclidean space Rd, and my set system is going to be the set of convex sets. Okay, so that's one version of the problem, which is called convex body chasing. Now, another version of the problem is, instead of a set system, I'm going to be chasing convex functions. So again, my state space is Euclidean space Rd, but now every time step, I'm going to get a convex cost function. These two problems are in fact equivalent up to, you know, moving from Rd to Rd plus 1 or something like that. All right, so that's what I mean by, you know, you don't gain any generality. All right, so this is again what we're gonna focus on. Is there any question on the setting, on the definition of the problem?
So that, I mean, just for one easy side of the equivalence, is it that the cost function is just the distance to the set, or?
Right. Sorry. So for the easy side, it's completely trivial, because, you know, convex functions, in particular, they can be the indicator of a set. So, you know, you can have 0 on a set at plus infinity outside, meaning that you better be in the set. So clearly,
right,
convex functions are more general than convex sets. And in fact, you know, I don't want to do it now because it's going to take, you know, 90 seconds, but you have also the other side of the equivalence. All right. Okay, thanks a lot for the question. This is really, really helpful, because it's hard to know, you know, especially since I don't see you, I don't know what you guys know, you know, I don't exactly know the audience. So please ask questions. Okay, so I'm gonna now tell you some results on this setting. Okay, and after that, my goal is really to teach you, you know, how to obtain those results. So I'm hoping that by the end of the lecture, you will know at least the basic of how to derive all the results on this slide. So here is the main open problem in the field, so to me at least. So the main open problem is that for arbitrary metric spaces, we believe that you can be log n competitive and that this is tight. Okay, so again, what is n? N is the size of the metric space. So if you have a state space of size n, and you're getting, you know, this set request, or you're getting cost function request, doesn't matter, it's the same thing, then we believe you can be log n competitive. What do we know? We know log squared n. So this is myself, Michael Cohen, James Lee, and Yintat Lee a few years ago. And we know that, you know, it's also almost tight, meaning that there is a lower bound of log n over log n. This is actually highly non-trivial, because it's a lower bound for any metric space. It's not like there exists a metric space such that blah. For any metric space, this is a lower bound. And this is two beautiful papers on, you know, the Ramsey theory of metric spaces. So this is Bartal, Lignal, Mendel, Naor. And this is Bartal, Bolobash, and Mendel. So these are very beautiful papers, highly recommended. I won't talk about lower bounds. I will only talk about upper bounds. Another thing that we know is what I just told you about for convex body chasing. So this is a case where the state space is just Euclidean space Rd, and the set system is a set of convex sets. Again, you can also think about a set of requests of cost functions as convex function. So this was introduced in Lignal and Friedman in '91, and they proved that you can be competitive for d equal 2. Then in later work by myself, Yintat Lee, Yuan Julie, and Mark Selke, we proved that you can be competitive in any dimension, and we got an exponential in the dimension competitive ratio, and this was not an easy result, but then it was simplified tremendously, and I'm going to give you a full proof of this result in one slide, in like 2 equations. So now we know that you can be D-competitive, and this was breakthrough work by Mark Selke and by Anupam Gupta with his student CJ Argue, Guru Ganesh, and Ziye Teng. And this O of D is tight for L infinity. Let me just make sure that we're on the same page by telling you why this is tight for L infinity. You know, imagine that you start at, you know, let's say row 0 is 0. Okay, you start at 0. And then what I'm going to give you as a constraint, you know, you're getting every time step, you're going to get a convex set, which is a constraint. And the first constraint, you know, K1 is going to be maybe that, you know, the coordinates, the first coordinate of 1 should be 1. Okay, or it should be -1. I'm going to choose either I'm going to give you, you know, the half space, which is at +1 on the first coordinate, or the half space, which is at -1 on the first coordinate. So you're going to move, you know, and you don't know where to go. You're going to move to the closest point. Then I'm going to give you, you know, K2 is going to be that row 2 is either 1 or maybe -1. I'm going to choose, you know, the worst case for you, either the +1 or the -1. So I'm going to fix the second coordinate now, and so on and so forth. Every time, as the online algorithm, you have to move a distance 1 in L infinity. You have to change one of the coordinates. But of course, what could the optimal algorithm do in hindsight? The optimal algorithm in hindsight can just, you know, set all of its coordinates correctly in one move. So in L infinity, opt is just paying 1, whereas you're paying, you know, the number of dimensions. All right, so I hope this is clear. Oops, what's going on? I don't know. Sorry, just a sec. Okay, I don't know what's going on, but okay, that doesn't matter. It erased itself. So, okay, so I hope this is clear. The lower bound of omega of d for L infinity. In fact, I'm going to show you this slide. Now, something that I'm very interested in, and this was the title of the talk, is set systems of small sets. Okay, and I will tell you why this is, to me, very interesting from a technical perspective, and I think it's also very natural just as a problem. So let's say you have a set system where all the sets are of size smaller than S. Then we believe, myself and Yuval Rabbani, that the tight answer in this case is S squared. And I will exactly explain to you why we believe this S squared. There is a very beautiful paper by Ramesh, which was published, I think, at SODA 91, which showed an upper bound of S to the 13 for this problem, and also a lower bound again of omega S squared. So we know that S squared is, you cannot really beat it. And let me say right away, and I will explain this in more detail later, is that this problem is really fundamentally different from getting, you know, the log n, for example, in the first bullet point. And why is it fundamentally different? It's because here there is no dependency on the metric space. The metric space, for all you know, it could be, you know, the Urison metric space, like that contains all the finite metric spaces in it. Okay, so you start with something like your data at the beginning is completely enormous. So you have to really adapt online, which is exactly the same difficulty as to get polylog k for k server. So, you know, Anupam talked about it in the previous talk as one of the main open problems. And what's difficult with getting polylog k for k server is that n, the size of the ambient metric space, does not appear. So this is the difficulty, and you will see why. So a kind of dual perspective is, you know, small set system of small sets. Okay, good. What about small set systems? I think this is very natural also. So let's say that your set system only has m sets in it. Then, you know, what happens in this case? So I'm not going to talk about this paper in detail. So this is a paper we had with Yuval Rabbani 2 years ago. And, you know, some very surprising things happened. So maybe just for the expert in the room, we showed that for the uniform metric, you can be M competitive and that this is tight. And for a 2-level HST, it's going to be exponential in M. And this is also tight. And what's really surprising is that it's the same answer whether you're deterministic or randomized. And as far as I know, people kind of thought that randomization always gives you an exponential benefit, you know, in online algorithm. And this is one case where it doesn't. You know, you don't win anything by randomization. And here again, the answer is very different if you consider a different parametrization. So instead of having a small set system, meaning that the adversary can only hit you with a few different sets, what if, you know, the adversary can only hit you with a few different functions? And there the answer is completely different. In fact, for uniform metric, m equals 2, only 2 functions, is enough to be as hard as any number of functions. So this is kind of, you know, maybe unexpected. Again, I won't talk more about it. If you want to ask me questions, maybe in the Q&A, I will try to leave time for questions at the end. But yeah, this is one thing that we understand. So for K-chasers, you can look at a K-chaser version of all of the above, and K-server is of course very famous, but this is to me just one example. K-server is really the most basic version of K-chaser for chasing sets, where the sets are singletons. But you can ask, what happens if I have K-chasers and maybe I'm chasing convex sets? And here's a surprise that I will tell you, I think very, very briefly, is that it's not possible, basically. As soon as you're in dimension 2 in the plane and you have 2 chasers, then you cannot have finite competitive ratio. And this is a story, a more general story that I'm going to try to tell you, is that basically there are canonical problems in this field where you can develop really beautiful tools for it. But as soon as you deviate from those canonical problems, things becomes impossible. And understanding exactly what this means, I think, is really a fascinating question. And again, another case in point is that as soon as you allow for free movement, okay, so sometimes some requests, they are free, then the problem will become impossible, even for convex. So this paper was myself, Yuval Rubani, and Mark Selke. This is myself, Niv Burbinder, Christian Koester, and Mark Selke. I will tell you about this. So now, okay, so these are the results. Any question on the results? Okay. If not, what the presentation will mainly be about are tools, okay? I want to tell you about the tools to solve these kind of problems because I think they are very general. They could be used for other things. So the first tool is something that Anupam talked about, which is that for finite metric spaces, you really want to reduce to 3 type of metrics. And usually this loses you a log n factor in the competitive ratio. And this is bad for K-server or for chasing small sets because you don't want a dependency on n. But okay, I will explain that. But at least for the finite case, I'm going to focus on trees. Okay, so for finite metric spaces, I'm only going to be talking about trees. I won't say more about this reduction to trees. This is very classical. Now, maybe more interesting and newer for some people. What happens here is that gradient descent or regular gradient descent, or alternatively / equivalently, and I will explain that, follows a perturbed leader. These seem to work well for this type of problem. And entropy functionals are natural regularizer because of the following property. So maybe, so this line contains a lot of information, and I'm going to come back to this line. I see that I'm going a little bit slowly, so I'm not going to explain this line right now. But this line is going to be explained in a couple of slides, okay? So I'm going to tell you why gradient descent makes sense for this problem and why entropic regularizer also makes sense. And again, once you understand, in fact, the reason is really just one line, which is this line. Now, so I'm going to tell you how to do, entropic regularization for chasing sets in finite metric spaces. But the problem is, you have to choose an entropy on your metric space. And for K-server or for chasing small sets, remember that the metric space could be, the universal metric space that contains all finite metric spaces. So you cannot start by saying, I'm going to define an entropy, which works for absolutely everything in the universe. That just doesn't make sense. So what you're going to need to do if you want to get polylog K for K-server or poly S for chasing small sets through gradient descent is that you will need to have an adaptive entropy functional. The set, you don't want to start with the whole set. You want to discover the set as you go. And this is what we have been trying to do with Yuval Rabani. And this is what James tried to do a couple of years ago. And as some of you know, now, there is a mistake in that paper. So right now, we still don't know polylog K for K-server. Was there a question? Did I hear a question?
Yeah. It was just, so what did you say Ramesh proved? Because I thought you had some like
absolutely. Yes. So Ramesh did prove poly S, but not through a gradient descent approach. So he had, he came, in the 90s, you can imagine, it was very combinatorial in spirit and very, very clever as always, a very clever potential, but extremely recursive. And he gets, yes, this S to the 13, which is really a tour de force. I don't know how he managed to do that. What people were doing back in the 90s for chasing small sets was exponential in S via deterministic algorithms, which is very natural. And he managed through randomization to reduce this exponential to polynomial. But I believe that, entropic regularization with an adaptive entropy is going to give you the tight S squared.
But do we have poly S using gradient descent-ish stuff?
No, so where what I have right now is exponential in S through gradient descent, but it's really like, you know, it's like the cheap, like at the end of the proof, you do something cheap and you get exponential. And, you know, if you just work a little bit harder, I believe you're going to get poly S and in fact, even S squared. But right now, no, and certainly there is nothing published on this. Okay, and the other point that I want to make, you know, in this presentation is that as soon as you depart from canonical problems, you know, suddenly things becomes very, very hard, and not hard mathematically, like literally impossible from a competitive ratio analysis standpoint. And this connects to very beautiful mathematical questions like ultra homogeneity. You know, maybe I will talk very briefly about that. All right, so let's get started on actual tools, how to actually solve the problem. And let's start with, you know, 2 centuries ago, the classical solution for the offline problem. So what is the offline problem? You know, I call this problem chasing because it's a nice name, chasing, but really it could also be called online selection. You know, at every time step, you're going to select a point. Now, selection problems, you know, meaning mappings with the property, you know, from a set system to elements in the you know, ground set, such that F applied to a set, you know, is in S. This is a selection map. This has a very, very long history. And a very classical question is to find Lipschitz selectors, meaning that you have 2 different sets. You know, your selector is going to select 2 different points in those 2 different sets, and you want this selector to be Lipschitz, meaning that you don't want, if the 2 sets are close to each other, let's say in Hausdorff distance, then you want the 2 selected points to be close to each other. And chasing is nothing but an online version. It's an online Lipschitz notion. Okay, it's exactly an online Lipschitz notion. That's all it is. Now it turns out that, you know, mathematicians, they are good at some things, and in particular they found the optimal Lipschitz selector for convex sets. Okay, so they didn't find, you know, the best, you know, the tight order or something like that, a big O and a corresponding lower bound. They found literally the most Lipschitz selector, and I'm gonna write this for you. So here it is. So the Steiner point is defined as follows. You input a convex body K, and it's going to output a point in this convex body as follows. So what I'm going to do is that I'm going to take a random direction theta, okay, a random direction theta on the sphere, and I'm just going to go as far as I can in this random direction theta while staying, you know, in the convex set. And now so this is, you know, an extremal point on my convex body. And now I just take the expectation of this with respect to the uniform measure on the sphere. All right, very, very beautiful object. This is clearly a selector. This, you know, by convexity, this point is in K. And it turns out this is the most Lipschitz selector. You know, you might wonder how in the world can you prove this is the most Lipschitz selector? I mean, this is a extremely high dimensional, infinite dimensional optimization problem, right? To search for all selector. So what happens is that basically this Steiner point has a lot of symmetries in it. And what you can do is that you can start with any selector and you can start to symmetrize it. And what you will see is that you only improve the Lipschitz constant. And eventually, if you symmetrize enough, you're going to end up with the Steiner point because it is the unique selector with all those symmetric properties. Okay, so of course, I'm not going to prove that now, but yeah. So good, this is great. So what you could, yes,
just
question?
Can you give one sense as to what symmetrizing would mean? If you want to symmetrize a selector, what does that mean?
Right, right. So what you would do is you would take, very, very simple, you would take perturbation of your set K. So for example, you know, one symmetrization, so maybe here is a different version to describe, which is kind of crazy. So you can increase the size of K. Okay, so you can add, you know, an L2 ball. So I don't know if I would call this symmetrization, but you can do some operation on your convex set K, like, you know, increasing it. And now you can take the center of gravity after having increased it like this. The Steiner point, another definition of it, which will, you know, I think show you some window into, you know, what would symmetrization be. Another definition of Steiner point is the center of gravity of the inflated body as the inflation goes to infinity.
Gotcha.
Yeah, which is crazy beautiful, if you ask me. But from that perspective, it's harder to analyze. So what I did here is that I gave you maybe, you know, the more optimization like flavor of the Steiner point. And this is also going to allow us to do a very, very simple analysis. So I promised to you, you know, to give you the D-competitive algorithm for convex body chasing. Remember, this was open for, you know, I guess 30 years. Is that correct? Yeah, 30 years. And then it turns out that the answer is 1 line. Okay, so I think this is also one of the lessons that I want you to take out of this presentation. There could be a very easy solution to all those problems. Okay, so let's do the analysis. So let me first just say this is a support function, right? You know, this is, let's call it hk of theta. Okay, so the value of this maximizer, this is a support function. I look in the direction theta, you know, what is the maximum for x in k of x dot theta? This is the support function. Now the Steiner point, you know, is nothing but the expected gradient of that function, right? Because, you know, if I have a max like this, you know, it's going to be maximized at some x. So the gradient is really just, you know, this x. It's just the maximizer. All right. So the Steiner point is nothing but the expected gradient of the support function. Now you can just do an integration by parts, and what you will get, you know, you integrate a gradient, so you will just get the integral, you know, on the surface of the function itself times the normal at that surface. So what you do is, instead of taking theta on the sphere, let's take it on the ball. Okay, so you have the unit ball. What is the surface of the unit ball? Is just the sphere. What is the normal on the sphere? Well, it's just the vector itself. Okay, at theta on the sphere, the normal is theta. So what I get is that the expected gradient is just the expectation of the function itself, hk of theta times the normal theta, and there is a factor d, you know, which has to do with the relation between the surface measure and the measure of the ball itself, right? When you move from one dimension to one dimension less. Okay, so these are equalities. This is just another definition. So now what I want to do for you is to show you an upper bound on the Lipschitz constant in the Hausdorff metric of this selector. And this one line is going to generalize to convex body chasing. So let's do it. So you have two bodies, K and K prime. And what I want to do is that I want to measure my movement. Okay, so I move from Steiner of K to Steiner of K prime, and I want to know what is the norm of the difference. Well, by definition, by this equality, it's just d times the expectation of hk of theta minus hk prime of theta times theta. Now I can just apply the triangle inequality, right, and bring, you know, the norm inside. The norm of theta is 1. So what I get is just this thing is just bounded by the expected difference, absolute value difference between hk of theta and hk prime of theta. Now it turns out that hk, you know, it is smooth in Hausdorff. I mean, this is kind of obvious, you know, maybe you just think about it a little bit. If you change a little bit your bodies, and of course the support function is just changing a little bit also. So what you get is that, you know, the L infinity norm of hk minus hk prime, this is smaller than the Hausdorff distance between k and k prime. So that's it. We have proven that this difference is bounded by d, which was the d from the integration by parts, times the Hausdorff distance between k and k prime. So this gives you that the Steiner point is d Lipschitz in the Hausdorff metric. And in fact, you know, this is not a tight bound. You can get a better bound, but this doesn't matter for us right now. Now, what I claim is that the exact same calculation is going to yield d competitive for the nested convex body chasing case. And this is what we did with Boas Kartag, you know, a couple of years ago. So why is that? Look at it. It's very simple. The only difference is as follows. So what I'm going to do now is, you know, I'm doing convex body chasing. So I get a convex body, then a convex body inside, then another one inside, and so on and so forth. And the way I'm going to chase is that I'm just going to move from one Steiner point to another Steiner point. Okay. So what I want to control is the sum for t equals 1 to capital T of the Steiner point of kt minus the Steiner point of kt plus 1. And the point is, because those things are decreasing, it means that the support function is decreasing. So the absolute value of hkt of theta minus hkt plus 1 of theta, I can remove this absolute value. I know exactly the sign of this. This is always non-negative. So now I'm going to have something summable. When I sum those things, I'm just going to get, you know, hk0 of theta minus hk capital T plus 1 of theta. I get something summable. Everything sums up. So at the end of the day, I'm just going to get that this total sum is bounded by d times, you know, the support function at the beginning, which is some constant. So I get that the total movement of my Steiner point is bounded by d. And let me say, this is really highly non-trivial. I mean, convex body, nested convex body chasing, you know, there were papers before we started looking at it, you know, by Nikhil Bansal and co-authors, which were giving non-trivial algorithm exponential in the dimension. And then we worked hard and we got something polynomial. But in fact, in one line, you get d-competitive like this. Okay.
Sorry, Seb, what do you do with the absolute values? I mean, the norm on the outside? Like,
yeah, excellent, excellent. So again, I have this norm right here. I'm going to use a triangle inequality, bring the norm inside. The norm of theta is 1. So I just get the absolute value of hk of theta minus hk prime of theta. And now here is the key observation, is that because this is nested, hkt is bigger than hkt plus 1. So I can just remove this absolute value. I know the sign.
I see. So I was just missing that part of the computation happens after you do the triangle inequality.
Right. Absolutely, exactly. Yeah, you do the triangle inequality, you end up with an absolute value, and now you say, oh, actually, you know what? I can remove it. Okay, excellent. So now the breakthrough work of Mark and Anupam et al., from my perspective, it's really to recognize that this previous calculation, you can redo it for the general convex body chasing case. It doesn't have to be nested. If you're clever enough to see the Steiner point as what is called in online learning, follows the regularized leader. And I say this parenthesis, this view may be more important than the selector view, because this paper by CJ Argue, Anupam Gupta, and Molinaro from a couple of months ago, they showed that some selectors might, which are Lipschitz, offline, might not be online Lipschitz, even for the nested case. So really the selector view is kind of misleading. What happened was really Steiner. This was the key, not the selector. It was Steiner the key. And the way you can see this follows the regularized leader view is as follows. So let's recall what is a work function, which is one of the most important objects in online algorithm. So the work function WT is defined as follows. It's simply the smallest distance. So the work function at a point X, in general, in some metric space for a chasing problem, it's the smallest distance that I need to travel in order to reach this point at time t. And now in the convex case, for convex body chasing, this function, it turns out to be convex. Why is that? It's because I can just average trajectories. If I have X and Y, and I know there is some amount of work that I need to do to get to X, some amount of work that I need to get to Y, this work is witnessed by two trajectories in the state space, but I can average those trajectories because any point, average on those trajectories is also in the convex request at any time step. So the average is a witness that, on the midpoint between X and Y, my total work is going to be less than half of the work to get to X and half of the work to get to Y. Okay, so this is a convex function. Now, so what I call this,
what is it?
Yes.
What is the input to the function exactly? Like, I mean, is it all the sets up until time t?
Exactly. Yes. Exactly.
Okay.
Yes. Thanks for the question. Yeah. So this is something you define online. As you go, you've seen a certain set of requests, and yeah, this is how you define it exactly. So now, what I call the Selke point is exactly the generalization of the Steiner point when you think of the Steiner point as a regularized leader. What do I mean by regularized leader? Really, what you would like, where you would like to be, is at the minimum of the work function. That's where you want to be. But, always being at the current optimum, this is very unstable. In online learning and, I'm sure in online algorithm also, we know this forever, just trying to optimize to be at the best point given what I have seen so far, this is very unstable, and it's going to lead you to move around like crazy, and you will not be online Lipschitz. You will not have a good competitive ratio. But what you need to do, and in online learning we do that all the time, is you need to regularize. So instead of just minimizing the work function, you add a little, potential, a regularizer. And what you do in the Steiner point case is that the regularizer is just a random linear function, and you integrate over those random linear functions. So this is it. This is the cell key point. And I'm not going to do it because I'm really way over time already, but you can repeat exactly the same analysis. This is it. This is the analysis, and you will see that this is decompetitive. Okay. So this is follow the regularized leader. Now I'm going to connect follow the regularized leader to mirror descent, and I'm going to tell you how to, connect to some previous work that we've been doing. I'm going to skip that. So this was, the fact that, okay, so you get decompetitive for convex body chasing, and it's, kind of canonical. All the calculations are super easy, but as soon as you deviate from the canonical setting, it becomes impossible. So if you have two chasers in dimension 2, then the problem is impossible. You cannot get a finite competitive ratio. On the other hand, if k is equal to 1, then you can do Steiner point. And if you're in dimension 1, then you can do double coverage. Okay, so this is a proof. We're going to skip it. In that paper that I mentioned before, we introduced a generalization of k-taxi, which is as follows. Between requests, you have contractions. So, you were requested on the set ST. You have chosen a point in ST, and now I'm going to apply for free a contraction. Okay, meaning that I'm going to map this entire set X. I'm going to remap it somewhere else into X, but this mapping is a contraction. So, everything gets closer to each other. So a priori, like at least naively, it feels like this should only help. You're only contracting distances. Like, if I was at a certain distance from opt, now I'm only closer to opt. What bad thing could happen? Well, even nested convex body chasing becomes impossible when you have contraction, when you have free contractions. Okay, so as soon as you deviate, it becomes impossible. There is a very long and nice story, which would take, probably an hour to tell you about this paper. In the end, for example, for k-taxi, we can get a polynomial in the size of the metric space, which is better than what was before polynomial in exponential in k. Anyway, we can talk about this maybe later. This is a proof. But now, let me, in the last 15 minutes, tell you about mirror descent and, how you use these ideas from the convex setting, how you use them for discrete problems, which is, one of the key points of this workshop. So let's go back to chasing finite sets. And in fact, let's go back to chasing functions. Okay, so we have a finite metric space X, and we're going to get cost functions on this finite metric space. And, we want to be competitive. Now we're going to, the randomized description is that we have a random point rho in our state space capital X. But I don't like to work with this, random rho like this. Instead, what I'm going to work with is that I'm going to work with a point X in an n-dimensional simplex, where n, is the size of the metric space. So n, it was the size of the metric space. Now it becomes the dimension of my problem. Now notice what is key is that cost functions, they become convex. In fact, they become linear in X, right? Because my cost, if I just have, the expectation of, of C of rho, and rho is from X. This is nothing but, the sum of X of, I, C of I for I, or maybe C of rho, like this. Okay, so this is just X dot C. Right, so my cost functions, they become linear in the representation in terms of probability distribution. I mean, what I have written is completely trivial. And now the movement cost, notice this is very important, it becomes a Wasserstein distance. So if I had a certain distribution at time t, and I have a new distribution at time t plus 1, what I need to do is that I need to find the optimal coupling between a sample at time t and a sample at time t plus 1. Okay, so the Wasserstein distance become my notion of movement cost. Now, what is this Wasserstein distance? Again, I told you that we're only going to look at trees. So let's look at what happens on a tree. So we have, our set of leaves. This is our metric space. And, we have X of L. This is the amount of mass that I have at location L. This is the probability that my chaser is at location little l. Now I can define, values for the inner node, which is the amount of mass in that node. Okay, so XU is just the sum of the XL for L in, for L in U, right? So XU is just the probability that my chaser is in one of the leaf in the subtree rooted at U. And now let's say my metric is given by edge weights WU. Okay, so the metric space is just this tree metric with edge weight WU. In this case, what is the movement cost? The movement cost associated to some, infinitesimal movement X prime is just the sum of the WU XU prime, right? If I want some amount of mass, maybe to leave, the subtree U, well, this mass has to go through the edge with weight WU. Okay, so clearly I need to pay WU times the absolute value of XU prime. In fact, this is all I need to pay. It's very easy to design a plan that will get you that movement. Now, here is the key observation. This is nothing but the L1 norm, weighted by W of X prime. So really, what did we do? What is the difference between, metrical task system, meaning chasing finite set in finite metric spaces with respect to convex body chasing or chasing convex function? Well, the difference, there are two differences. The first one is that now we have an L1 constraint instead of the L2 constraint that we had before. And at least from the online learning perspective and also in optimization, you hope that when you move from L2 to L1, you can maybe replace the dependency on the dimension by maybe log of the dimension, which is exactly what we're trying to get. Now, this is not at all the full story. In fact, just replacing L2 by L1, we have proven also in a previous paper that you will still depend polynomially in N. Okay, you will still have a square root N competitive ratio lower bound. So it's not just about replacing L2 by L1, but it's also about the fact that the cost functions are now linear instead of being convex. So this combination of having linear cost function and L1 metric instead of L2, this is what's going to allow you to have a poly log N instead of a poly N competitive ratio. Now, let's see how we're going to solve this problem. Let's take what we have understood, which was canonical, namely convex body chasing or convex function chasing, using a regularized work function. Okay, so we had our work function and we added, a random potential and we took the expectation. And the analysis was kind of miraculous. Why do I say miraculous? Because again, it's not like an arbitrary selector works. Okay. Now, in essence, and this couple of lines are very important. In essence, again, this is just follow the regularized leader, meaning you minimize the work function plus the regularization. Now, what does this mean? This means that at the minimum, because everything is convex, you are at a critical point. So the gradient of phi of x is equal to minus W. Okay. Now, what does it mean incrementally? Incrementally, if I differentiate this thing, and sorry, it should be gradient of W. Okay, I'm sorry about that. Which means incrementally, if I take a time derivative of this, what am I going to get on the left-hand side? The time derivative of the gradient of phi is nothing but the Hessian of phi times x prime, and this is going to be equal to minus c, where we're going to say that W prime is equal to c. Okay, so c is a cost function, and this is actually very, very delicate, and I'm maybe going to explain one sentence for the expert. But let's say in general you get this equation. You get that the Hessian of phi at x times x prime is equal to minus the cost vector, and this is a mirror distance equation. Now the key point is that there is a miracle, and I have 9 hours of lectures on YouTube on this, so I'm not going to be able to explain those 9 hours in 5 minutes. So you can take a look if you're interested. But the first miracle, the key point, is that mirror descent comes equipped with a potential immediately. And what is the potential? The potential is a Bregman divergence between y and x, which is this formula. And if you just look at the time derivative of the Bregman divergence, it's a one-line calculation. What you will see is that the time derivative of the Bregman divergence is minus the cost times y minus x. So for any comparator y, what you have is that, look at the following. If x pays more than y, okay, so if c dot x is bigger than c dot y, if you're paying more than y, then this is negative. So that means that the Bregman is decreasing. So if you're making a mistake online, you know, you're paying more than some other point y, then you're learning about y and you're converging towards y. Okay, so this is a key point of mirror descent. So from our perspective, this is going to mean that the service cost is automatically bounded by opt. And so all you have to do is to analyze the movement cost. And, you know, here's a very important note. This is not quite correct. This assumption that, you know, the cost is in fact equal to the derivative of the work function is not quite true. But in fact, it is true if you assume that your potential phi is 1 Lipschitz. And this is critical and related to what Ola was talking about in his presentation when he was talking about primal dual algorithm. And he was saying, you know, you multiply by 2 and then you add 1 over, you know, the set cover size. The plus 1 over the set cover size is exactly the fact that you need this phi to be 1 Lipschitz. These are the same phenomenon. I won't have time to say more than that. Okay. Now you get into entropic regularization. Why is that? It's because you automatically control the service cost, but you would like to control the movement cost. And this is where it becomes natural, because what is the movement cost? The movement cost is the Hessian phi inverse applied to your cost vector and the L1 of W norm. Now, if you use a potential phi whose Hessian is equal to, you know, some learning rate time, something which is diagonal of W over X, then look at what happens. The inverse Hessian is X over W times C. Now the 1 over W cancels with the L1 norm of W, and what you get is that this movement is exactly X times C. So if you use a potential which is this one, then your movement cost is exactly equal to your service cost. Your service cost times the learning rate eta. Why does eta matter? Because, you know, what is a phi that gives you this Hessian? Well, a phi that gives you this Hessian is exactly the, you know, entropy, so x log x with a W in front, and now you have a 1 over eta, and you want this to be Lipschitz, remember the previous slide. So what you're going to add is a little bit of regularization, a little bit of shift inside. So this, if you add 1 over n shift and you normalize by log n, then this is 1 Lipschitz, and you get log n competitive because of eta. Now, this is almost it, okay? This is almost the state of the art on this problem. The only thing that I didn't tell you is that now, because you had to add this eta, you know, to make phi Lipschitz, there is an extra movement due to delta. And also one thing that I didn't tell you is that there are some constraints, you know, that lead to some extra movement. And this extra movement gives you an additional log n, and that's why we get log squared n. Okay, very good. So that's, you know, there are hours and hours of lectures on this online, you know, or yeah. So I won't say more. So far I have told you, I think at least somewhat convincingly, is that you can be D-competitive with follow the perturb leader on work function for convex body chasing. You can get log cube n for metrical task system. I told you 1 log n is the HST embedding, 1 log n is the canonical log n, and an extra log n is the movement from the Lagrangian. In fact, you can even get it down to log squared n, and this is a very nice paper of Christian and James. And, you know, the same ideas give you this log n times log squared k for k servers that Anupam was talking about. Now, the question is, can we push these techniques to get polylog k for k server and poly s for chasing S size set? And in those cases, the key point is that you just cannot hope to build a 1 Lipschitz regularizer on the entire space. That will just be meaningless. So what you need to do is you need to adapt your entropic regularizer. But as you adapt your entropic regularizer, you will need to tell, you know, you will need to account what happens when the potential itself is changing. And there, you know, the form of the potential is going to be important. So far, the form of the potential was kind of irrelevant. You know, I just told you there is this Bregman divergence and it's automatically decreasing. But as soon as you move to the case where the potential is changing, the form of the Bregman is going to be very, very important. Now, let me just, in 3 minutes, give you a first look at adaptivity. So this paper is Fiat, Foster, Karloff, Rabbani, Ravid, and Vishwanathan, and they showed that chasing small sets is equivalent to layered graph traversal. What is layered graph traversal? The adversary selects a tree of depth capital T with at most k nodes per layer, and each edge has a weight which is either 0 or 1. At each round, the teeth layer is revealed to the player, and the player must select one node in the layer. What is the cost? The cost is just the number of edges that you have to traverse to attain the newly selected node. I mean, number of edges with cost 1. So just to clarify, let's say this is a tree, and let's say we were at times 3, and at times 3 we are at this location, and now I reveal to you the next layer, this one. So now you cannot continue. You're blocked. This is a dead end. So you have to backtrack like this to get to the next layer. So your movement is going to be 1, 2, 3, 4, 5. So you're going to move 5 steps at this point, okay? Whereas, of course, Opt knew that, and Opt was here and just moved 1 step. Okay, so the question is, can you be competitive in this case? And K and S are basically the same thing. Okay? So what I want to say is that ignoring the dead ends and the splitting and all those complicated topology updates, this is more or less exactly the tree case that we had before, but where the edge weight is growing over time. Instead of the metric space being fixed, the edge weights are changing online. But now the movement cost is decomposed into 2 terms. What happens is that you add mass X at at distance W, and really we want to know how is this changing over time. Your movement cost is really the time derivative of this in L1 norm. But now there are 2 terms by the chain rule. This is going to be X prime W plus X W prime. So really this thing is X prime in L1 of W plus X times W prime. So you see, this is exactly what we had before. This is your movement cost on the metric space, which is not changing, plus a service cost, where the service cost, the cost function is exactly the increments of the metric. So you can apply exactly the same calculation as before and hope for the best. Now, what you have to do is you have to take into account how your Bregman is going to change when W changes. And now up to some minor things, what is your Bregman? It turns out it's just a relative entropy. So it's a sum of WU, YU, log YU plus delta U over XU plus delta U. And now morally, and this is, this sentence is a key sentence that gives you hope that everything eventually is going to work out and the world is going to be great, is that when W is changing, this quantity only changes by W primes times Y times, this log, but this log can only be as big as log 1 over delta. But W prime times Y is exactly how much Opt is paying right now, right? It's the increase in distance of Opt. So the increase of the potential, the change in the potential is nothing but Opt times log 1 over delta. So it seems like everything is going to be okay. You're just going to get an extra log 1 over delta. Now it's, this is true. And, because we knew that you can be competitive with respect to the combinatorial depth here, if you do some minor things, the combinatorial depth in layer graph traversal is always going to be smaller than K. So you hope that you can get K log 1 over delta competitive, and delta will need to be exponentially small in K. And, these are some good reasons for that. So that's why you hope to get K squared. Okay, K times log 1 over delta, and delta is going to be exponentially small in K. All right, so this was, very fast. And of course, here again, there is at least an hour to get over these equations. But maybe I can take a question or two. The conclusion is, despite several decades of work, many of the most basic questions in this field are open. There could really be an easy solution to all of them for real. Let's try to find it. Okay, thanks.